طيب بسم الله الرحمن الرحيم. Let's start the lecture. Hopefully this platform is going to work for us. Basically, we're going to meet on the regular times, the regular class times here on Zoom. We're going to start exactly at 1. I would suggest that you try to maybe join a little bit, like a few minutes before 1, so that we can start exactly at 1. If it's a problem for you all to start at 1, maybe we can delay it a little bit and basically we finish a little bit later, okay? So just let me know, okay? So today we're going to start talking about resistors. Basically, we're going to start with the concept of conductors and insulators. By the way, feel free to ask any questions in the middle of the lecture, please. You have the audio, you have control over your audio, so just turn on your audio and ask any questions you want anytime, okay?
Okay.
So for the conductors and insulators, basically, if we do an experiment where we measure the resistance of rods made of different materials, for example, rods made from metals, we're going to find that these rods permit reasonable currents to flow. If we have rods made from non-metallic materials, like for example, if we make insulators, use insulator like glass or rubber or plastic, things of that sort, you're going to find that basically they permit virtually no current. So basically, insulators basically do not allow current to flow, or at least make the current flowing very small to the extent that it can be considered as zero current. But usually, this classification is usually oversimplified, because you cannot say that a particular material can completely stop the flow of current, and you cannot say that a material can freely permit the passage of current. So basically, you have degrees of obstruction and degrees of permeability. Okay, so basically, not all metals conduct the same, and not all non-metals prevent the current or insulate the current the same. So for example, if you have conductors, copper is a better conductor than steel, for example. And basically for insulators, you have different degree of insulation depending on which insulator that you're using. So basically you have variability among insulators and you have variability among conductors. Between the two, actually, you have the semiconductors, which all of you maybe you already have heard of. Basically, semiconductors can sometimes conduct current, sometimes they do not conduct current. So basically, we are somewhere in the middle. If we start talking about resistance, we have to talk about the concept of resistivity. So basically, certain materials permit the reasonably free passage of electric charge and are termed conductors, while others oppose such a free passage and are termed insulators. Basically, if you talk about a particular resistance, so the resistance will be equal to rho, which is the resistivity, times L, the length of this conductor, over A, the cross section. So basically, the resistivity or the resistance depends on the resistivity, depends directly proportional to the length of the conductor, and inversely proportional to the area. And the resistivity actually varies a lot between different materials. For example, if you have aluminum is like 2.7 times 10 to the minus 8. Basically, if you look at the units of this, this is basically you have here area, you have here length over area. So basically this thing here is like meter minus 1, and you have this resistance in ohm. So basically the resistivity will be ohm per or ohm meter, basically, because this is meter minus 1. When it goes to the other side, it's going to be meter. Okay, so maybe you can write it down. So basically here you have ohm, and basically it's going to be equal to rho times meter over meter square. So basically this times this, and basically multiply this by this. So basically the units of rho will be ohm meter. Okay.
Okay.
So basically, if you look at the materials, different materials, aluminum will be 2.7 times 10 to the minus 8 ohm meter. Brass is going to be like 7.2. Copper 1.59 times 10 to the minus 3, 10 to the minus 8. So basically, you have very wide variation. So see, for example, here the carbon is much larger. So basically, it's closer to an insulator than a conductor. So basically, you have wide variability among different materials. So basically, let's take an example for that. If we have a conductor of a diameter of 0.5 millimeters, and it has a resistance of 300 ohms, find the resistance of the same length of wire if its diameter were doubled. So here we don't have the area. Basically, we don't have the area. Let's just erase that. Basically, we don't have the area. D is not known. And basically, you don't have the resistivity. It's not known. But actually, you're comparing two different situations where in one of them, you have the same length of wire in both of them. And basic diameter between them was doubled. So basically, if you look at the equation, rho R equals rho L over A. So basically, if you have R1 and R2, and it's exactly the same material, it's exactly the same length, it's going to be R1 over R2 will be equal to rho L1 over A1 over rho L2 over A2. Basically here, rho is exactly the same between the two, and L is exactly the same. So basically it's going to be A2 over A1. And you have A is equal to basically pi d square over 4. I'm not sure exactly why it does that, but let's live with it. So basically this is proportional to d square, to the square of the diameter. So basically the ratio of the resistances will be the same ratio of the diameter square. So for example, let's delete that. So basically, if I have R1 over R2 equals to D2 square over D1 square, this means that if I double one of them, if D2 is double D1, this means that this will be 4 over 1, which means that the resistance, if the resistance R1 is equal to 300, or for example, yes, if this is like 300, then R2 will be what? Will be the same value over 4. So R2 will be 300 over 4. So basically in this equation, this problem, all we had to do is just consider the basic equation for the resistance as a function of resistivity and length and diameter. And given that it's exactly the same material, so the resistivity will be the same. It has the same length, so L will be the same. So basically the ratio between the two resistors will depend on the area. And the area is dependent on the diameter square. So basically the ratio will be dependent on the diameter square. And of course, it will be the opposite, like R1 over R2 equals to D2 square over D1 square, because basically the resistance depends inversely on the area, not proportionally, or not directly proportional. Is that clear?
Yeah, clear.
Okay. Here is a simpler problem. Here you have a coil wound from a 10-meter length copper wire having a cross-sectional area of 1 millimeter square. Calculate the resistance. In this problem, actually, you need to get the rho. You have to get it from the table. I'm not sure exactly why it does that, but let's try to live with it. Basically, you have to go back to this equation here, this table here, and get the value for rho of copper, which is this, basically, and just use it there, and that's it. Just use it and plug everything in. See, this is 1.59 times 10 to the minus 8. So basically, this will be, let me try to use
Doctor, are you going to give us the table in the exam, or do we have to memorize all of it?
You forgot that you have to, you basically can prepare a piece of paper for each chapter. So basically, you put anything you want in that paper. If you want to put that table there, it's fine. If you want to memorize it, it's up to you. Okay. So basically, it's up to you to do that. Okay.
Okay. Yeah.
So basically, here, we're going to use exactly the same equation. R equals to rho L over A. And basically here, we just got it like 1.58 10 times 10 to the minus 8 ohm meter. And L here is what? L is 10 meters, so actually it can be like this, just 10, because it's SI unit. And the cross-section area is 1.0 millimeter squared. So we have to convert that to what? We have to convert it to meter square, right? So we have to multiply by what?
Minus 6.
Minus 6, right.
Minus 6.
Right. So just compute that and that's it. Is that clear?
Yeah.
Yes.
You probably saw that equation before somewhere, right?
Yeah.
The equation for the resistance. It's very straightforward. Okay. Yes.
And the first question, the diameter D2, how come it's 4?
The diameter is double. One of them is double the other.
Double, yeah.
Basically, okay. So basically, it's right there. Diameter we're doubled. Okay. So basically, everything is exactly the same, except that basically the material is the same, the length is the same, but the diameter changed to be double that of the other one. So basically, you're gonna find that R1 over R2 will be equal to basically D2 square over D1 square, because basically the area is pi D square over 4. So basically, pi over 4 will basically go between the two, the upper and numerator and denominator, and basically D square will remain there. Is that clear?
Yes, okay.
Okay. Oh, sorry. Okay. So now we're going to start talking about some of the things that are kind of new. Okay. They are not very new, but actually many parts of them will be a little bit new to you. Okay. So, for example, practical code for the resistors. Okay. We know that if you have a resistance that has 4 bands like this, we know how to calculate its value. It's basically going to be like we get the code for the first one and the second one and make a number and basically have 10 to the power value of the third color, and basically the fourth color will be the tolerance, right? You saw that before.
Yes.
But how about if you have 5 bands, if you have 6 bands, okay? What would be the way to calculate the value of the resistance? Actually, the most general case is that if you have 6 bands. In that case, you will have 3 numbers, and the fourth one will be the multiplier, 10 to the power, the digit in the fourth color. And then the fifth one will be the tolerance. And the sixth one will be what's called the temperature coefficient. We're going to talk about it in a little bit. So basically, this tells you how the resistance changes with the temperature. Okay. So basically here, if you have, for example, if you have here, it's red is here like 2. You have here magenta or violet here is 7. And you have here yellow here is 4. And basically here you have black is 0. So basically it's 274 times 10 to the power 0, which is 1. And the tolerance here is red here. If you see the tolerance here is basically, we're talking about tolerance here is
2%.
basically we have 2%, basically, yes. And the black here, meaning that you have 250 parts per million per Kelvin. Okay, maybe we should talk about this a little bit just to clarify it for you. It's a little bit strange unit that probably you haven't heard about before. 250 ppm per Kelvin. Okay, so basically let's try and basically explain it a little bit. I'll explain it on a whiteboard. Basically, if you have a resistance value of, for example, 100K ohm, okay? Basically, if I say that I have a temperature coefficient of 250 ppm per Kelvin, It means that parts per million, meaning that basically this is going to be, the change will be 250 over 1 million times the value of the resistance, which is 100K, and all of that per degree Kelvin, meaning that you're going to add this value here for each degree Kelvin increase in your temperature. Okay, so basically this parts per million, meaning that basically this value here is multiplied by 1 to the power 1 over 10 to the power 6. Okay, so this is like, for example, ppm compared to percent. Okay, percent is 1 over 100, right? ppm is what? 1 over 1 million. Okay, so basically if this is ppm per Kelvin, it means that the resistance will increase by this ratio or by this factor from the original value for each degree Kelvin. So for example, if the delta T of delta temperature was like 10 degrees centigrade, which is exactly 10 degrees Kelvin, it's exactly the same, then the change in the value of the resistance, of this resistance in particular, will be 10 times this. So basically, maybe you can see how it is like 10 to the power 3 here, 3 here, and you have 0 here, make it 2 here, and also 1 here. So basically, it's gonna be, and this also with this, so it's gonna be 250 ohms change. So for 100K, it's gonna add 250 ohms after temperature increases by 10 degrees Kelvin. Is that clear?
Yes.
Yes.
Doctor,
Yes.
how 10 C equal 10K?
Basically, it's the delta T. It's a delta T. So basically, it's a difference. It's not absolute value. So basically, as long as it's a delta T, they are exactly the same. Okay. And actually, when we talk about the temperature coefficient in a short while, you will find that basically the temperature coefficient is given per degree centigrade. And basically, this is because that you're talking about a reference to a particular reference temperature. Okay. Here, if you talk about delta T, it means that if you increase the temperature by this value, which is exactly like this value, because when you subtract the 273.2 something, okay, basically it's going to be subtracted between the two, and basically it's not going to be there. So this is equal to this.
Thank you.
That clear? Okay, so let's go back.
Doctor, there's question.
Yes, go ahead.
No, I said there's question in the start about the example you said before.
Okay, go ahead. What was the question?
Someone is asking in the chat.
I actually can see the chat while I'm having I can see the chat now.
He said,
yes, go ahead.
He said repeat that step one more again.
I couldn't hear you clearly. Can you repeat, please?
What, doctor?
Okay. Let's just a second. One more again, please. The last step in what? In the problem in the we talked about the 250 ppm per K.
Yes, doctor. Can you give us a different example, like different numbers, just to make sure we have it?
No problem. Okay. Okay. Let's talk about a different example, like if you have 100 ohms. Okay. And this 100 ohms is basically measured at, for example, 0 degrees centigrade. And basically, you have a temperature coefficient for this resistance as 100 ppm per K. Okay. I need to know R, the value of R at temperature equal to, for example, 30 degrees. Okay, so basically this means that for each degree Kelvin, you will have an increase of 100 over 1 million times the resistance value per degree Kelvin. So if I increase by the increase is like 30 degrees, which is basically, as I said before, delta T is equal to 30 degrees Kelvin equals to 30 degrees centigrade, because it's a difference, it's a differential temperature. Then basically the new temperature at 30 degrees will be equal to R plus basically the same R times 100 over 1 million, okay? And basically this will be what? This will be basically, this is going to be like 100 if you remove these two. So basically going to be 100.01 ohm. Is that clear?
The delta temperature.
Sorry. Right. You're right. I'm sorry. Okay. So basically going to be like 0.3. Sorry. Okay, you're right. Is it clear?
Yes.
Okay. Let's go back to the presentation. So basically, the six bands will go like this. If you have only 4 bands, then you're gonna go with whatever you had in the lab before, or the way you measured your resistors before, which basically is gonna be the first 2 digits times 10 to the power 3rd digit, and basically the 4th band will actually give you the tolerance, which is gonna be usually either gold or silver, basically. It's gonna be either 5% if it's gold or 10% if it's silver. Okay. If you have 5 bands, then you will have basically 3 numbers times the to the power of the 4th. Okay, so here you have 3 numbers, 100 times 10 to the power 4th one or 4th band, and basically you have the tolerance in the 5th band. Okay, usually you will have if you have 5% resistance or 10% resistance, we have tolerance of 5 or 10%. You usually have only 4 bands because you don't really need 3 digits for your resistance, because it's actually its accuracy is not that high. When you have a 1% resistance, then you will actually need 3 digits so that you can describe the value of the resistance more accurately. Okay, so usually you have 5 bands if you have like 1% or higher than 1% tolerance. So basically for the 1%, maybe 2%, also 0.5%, 0.25%. 0.1, yeah, something of that sort. Basically, usually you'll have 5 bands. Other than that, the common resistors that you're gonna find in the lab are usually like 4-band resistors. Okay. If you look at the resistance in a circuit, you might find it basically looking like this. Basically, it might look like just a block like this, like a fixed resistance, just like basically just like a rectangle like this. You might find it in the usual resistance drawing form like this. You might find it like this if it's variable, and you have a difference between these two. This is like a variable resistance. This is the rheostat. Basically, they have the same value, basically the same basic function. And you might have it like this with 3 terminals if it's potentiometer. Okay, so the difference between the variable resistance or rheostat and potentiometer is that in the variable resistance, you have only 2 terminals. And basically, when you change the value of the resistance, it's just a resistance with a different value. Here, basically, the resistance between one terminal and the middle terminal, or the one that you move, okay, is basically what changes. The value of the resistance between this terminal and that terminal remains exactly the same. So the potentiometer has 3 terminals. A variable resistor or a rheostat has 2 terminals only. One very important thing also is how you find the label for the value of the resistance in a circuit. Okay, if you have a resistance of 0.47 ohm, you might find it marked as R47. There is a difference between R, K, and M. Basically, consider R as basically the decimal point here. If the number is to the left or to the right of R, then it's basically 0.47. If it's 4R7, then it's 4.7 ohm. If it's 47 ohm, then it's going to look like 47R. If you have 470, it's going to be like 470R. Okay, so basically R means that it's a multiplication of 1. Okay, and basically anything to the right of R will be a decimal point, will be basically like decimal numbers. If it's in kilo ohm, then you use K instead of the R here. So basically 4.7, you just put instead of the point here, instead of the decimal point, you put K. And you put it K capital, by the way. You don't put it K small, by the way. And if you have 47K, then it's going to look like 47K, exactly the same. But K here is basically is capital K, not small k, like the standard for K that we use in the SI units. If you have mega, it's exactly the same. You work with the mega exactly the same way. Okay, so let me give you some examples here on how to use that.
Doctor,
Yes.
I have question.
Yeah, go ahead. Go ahead.
On the previous previous slide.
Yes, you go ahead. Go ahead.
No, I need to know why you say there is 2 terminal in variable resistance.
Okay.
But there is three pins or
basically it's like this. Okay. Okay. What you see is this terminal and that terminal only. You don't see anything inside of the resistance. Okay. So basically, you have no control. You have no access to this. You don't have access to this one. Okay.
Okay.
The potentiometer is different. Potentiometer has 1, 2, 3 terminals. And the resistance between these two or these two changes when you change the position of the pointer. We're going to talk about it in a short while. And the resistance between these two is actually fixed. Between 1 and 2 is fixed. This is variable, and this is variable. Okay. Here you have just one resistance. Okay. Between this terminal and that terminal, it's always variable. Okay.
Okay.
Let me give you some examples. If I have, for example, 470K kilo ohm, how can I write it with M? If I want to put this with M instead of K. For K, I can write like the 470K.
470 M
M.
Put it on the right.
M47.
M47. So,
Yes.
right, right. How about if I have 0.1 ohm?
R1.
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 R1, right. How about if I have 10 kilo ohm?
1K.
10K. How about if I have 100K? I can write it as 100K
Okay.
or
M100.
M1, just one.
No, M1.
Okay. This is very important, by the way, because usually you find things like 4R7. This is very common. You find it very commonly in circuit boards. Okay. If you have a circuit diagram, it's very common to use this notation. So sometimes you see something like this, you don't understand what it is. Okay. You don't know what the value of the resistance is. You have it like it's labeled, it's written like this, R1, it's R1, and it's written like 4R7. It doesn't make sense. It's already labeled here as R1. Why should I label it as 4R7 here? It's actually, this is a value. Okay. So it's very important to know that notation and on that convention in circuit labeling, in the label of the value of the resistance. Okay. Okay, so sometimes the resistance is linear, sometimes it's non-linear, by the way. Okay, so basically, usually the resistance, unless otherwise specified, it should be linear. Linear meaning that the current and voltage across the resistance should be basically proportional to each other. Okay, sometimes basically it's always like that, but sometimes the resistance itself can have a nonlinear effect where basically if you put a different current, if you put double the current, for example, you're not going to get double the voltage. Okay, so basically these are called nonlinear resistors, and basically these are resistors made from semiconductor devices. I'm going to talk about some examples of these in a little while. We talked last time about the resistor series, okay, and we talked about the E12 series, which is the most common series that you will find in the lab, and basically it's designed such that for the E12 you have 10, 12, 15, 18, 22, 27, 33, 39, and so on until you have, again, you have 100. Basically, you have these values. You have 10 times these values. You have 100 times these values. You have 0.1 times these values. You have all multipliers of these values, basic times 10 to the any power. Okay, times 10 to the power 1, 2, 3, times 10 to the power minus 1, and so on. And the idea behind this is that the plus minus 10%, if you basically take the value of the resistance and put at plus minus 10%, the values are designed such that each resistance has a range that minimally overlaps from the range with the range of the other resistance. So basically, as you see here, it has very minimal overlap with the value from 82, from the plus minus 10% from the 82. And this has also minimal overlap with the plus minus 10% from the 68, and so on and so forth. And actually, this is the most common, but actually the smallest series actually is E3, which is if you have a resistance of plus minus 20%. For the 20%, you have only values of 100, 220, and 470. That's it, okay? And basically, you can imagine that you multiply these by 10 and 100 and 1,000 and so on and so forth. If you have plus minus 10%, you add another 3 values. So basically, in the middle between each 2 values, you'll find another new value. So we have here 100 still there, 220 still there, 470 still there, but you added 150, 330, 680. For the E12, you have exactly the same values here, but you add values in the middle. So basically, you have 100, you have 150, and so on. You have in the middle here, you have 120, which is like the 12 here, okay? So you have 12 values that basically span the same range, basically with the plus minus 10%. For the 24, it's exactly the same. All the values from the E12 series are there, with addition to basically here, for example, between the 100 and 120, you have 110, because here you have a smaller tolerance. So basically, you have a smaller range here, so you can add another value between this one and this one. You have also for E48, you have also E196, which is basically the plus minus 1%. Okay, so as you see here, for the plus minus 1%, you have many more values, like 96 values, and basically you will need to have 3 digits to describe the values. Here you don't need, basically for the E12 series, as you see here, you can describe them in just 2 digits. So that's why all resistance in the E12 series or below need only four bands in the resistance to identify the value. If you go beyond that, if you go to the E24, if you go to the E96, for example, you would need 3 digits in order for you to describe the small differences between the different values. For example, here you have 121, 124, 127. The first 2 digits are 1, 2. So basically, if you have only 2 digits to describe these values, basically you're not going to be able to distinguish between 121, 124, or 127. So these are the kinds of resistances where you actually need the 5-band or a 6-band identification for the resistance. Is that clear?
Yes, clear.
Yes.
Okay. So let's take an example. If you have a resistance of basically, if you have the first band as brown, the second band as black, the third band as orange, and you have no other bands. Basically, if you have no other bands, you have only 3 bands, basically you're talking about a 20% resistor. So basically, if you don't have any other band, if you have only 3 bands, then you have 20% tolerance, okay? So basically, this means that you have a 20% tolerance. We need to go back to the table to identify these. Basically, if you go back here for the first digit, basically it's black. It's the first one is brown and black. Brown here is 1, black here is 0. And the third one is basically the tolerance, the multiplier is orange. Orange is 3. So it's 10 times 10 to the power 3, which is what? 10K. Okay? Is that clear?
Yeah.
One very important topic that I actually added to the previous lecture was talking about the component leads. We have to talk about 2 main types of components, which are the through-hole components and the surface mount components. The through-hole components basically have leads that have to go through the electronic board, the printed circuit board. Basically, in order for you to attach this resistor to your printed circuit board, you have to actually get this lead inside the printed circuit board and basically solder it from the other side. Okay, you probably saw these, basically all the resistance that you saw so far are actually from this type. These are exactly the same type that you use in your breadboard. Okay, so these are called through hole because actually you have to reattach to a printed circuit board through a hole. You have to basically implant them in holes inside the printed circuit board. The problem with that is, you know, as you know, for the modern printed circuit boards, for example, if you talk about a computer, you have so many connections, you have made so many basically tracks that you have to connect, you have to use to connect components to each other. It's very difficult to use a board that has holes because it's really difficult to basically connect very high density components to each other when you have holes in the printed circuit board going from one side all the way to the other. And also we have now multi-layer boards, and the multi-layer boards usually have tracks that are running below the components, so that you can basically resolve the overlapping tracks and things of that sort. So basically these are very inconvenient. Usually if you use through-hole components, they are usually used for either a very old circuit or a very simple circuit, or if you want to do prototyping on a breadboard or anything like that. If you want to do some really modern printed circuit board and basically use or make the printed circuit board as small as possible, or basically if you have multi-layer board, then you have to use what's called surface mounted components. Surface mounted components basically are soldered at the surface of the printed circuit board. So basically they have these sides right there are made of metal, and basically you put some solder right under them, and basically they are attached to one surface of the printed circuit board. So basically on one side of the printed circuit board you might have a component like this, from the other side you might have another component in the same location soldered to the other side, and they are not connected to each other. Okay, and you have different sizes of these, and basically they have also a code that they use to identify their values, and it's very similar code to what you saw before. So for example, R100, what would be the value of this resistance? R100.
0.1.
0.1, right. How about 10.3? It's different now, okay? 10.3, if you find it like this, if you don't find R or K or M or anything like that, then we're gonna go back to the same code that we used before. So basically gonna be like the first 2 digits times 10 to the power third digits. So 10.3 is going to be what? 10 times 10 is going to be like 10K. Okay. How about this?
5.6.
5.6.
5.6 ohm.
Yeah.
How about this?
3.2.
39. 30.
390 ohm. 39 times 10 to the power 1.
Oh, 309.
How about this? 151.
151. 15 times
151.
150.
150. Yeah. 150.
okay.
Yeah. 150.
Basically, if you have R, if you have, for example, if you have 151 R, then it's 151. But it's just 151 without any R, then it's 15 times 10 to the power 1. Okay, how about this?
Okay.
47.
47K.
47K, right? Correct. Okay, let's give some examples of certain packages where resistors come. Basically, I want to first of all want to show you examples of different sizes of surface-mounted components. So basically, you can have resistors in what's called 1206 package. It looks like this. So basically, this is like a ruler so that you can know exactly the size of this component. And you can have exactly the same resistance in 0805 component. So basically, it's exactly surface mounted also, but it's a smaller package. You can have it as 0.603, 0603, or 0402. See how 0402 looks like? This is the kind of components that are used in such things as your mobile phone circuit board. You don't have that much space actually to put resistors of much larger size. And usually you need the large size of the resistance if you have power dissipation and you want to have a surface area where you can actually dissipate the heat that is generated from the resistance. If you're talking about the resistance used in a circuit board that is not intended for power, it's like intended for signal, then you don't expect to have any problem with power. So you don't have to have basically a large power, or you don't have to have a large component in order for you to dissipate the heat. So basically you can use very small packages like the 0402 like this, in order for you to have a very small circuit board. So you can have thousands of resistors in a very small package like centimeter by centimeter or something. See here, this is just an inch, okay? So basically you can put like maybe 500 of these maybe in a 1 inch by 1 inch board, okay? There are other packages that are like for a small outline package. This is basically a surface mounted board, but actually it's like you have the leads here. It's very similar to the DIP package, it's D1 inline package. This is what you're used to in your electronic components. This is what you use in the breadboard. Instead of having the leads going like this, like down like this, you actually have it basically, maybe I can draw it for you. So basically the component will be like this from the side, and basically instead of looking like this, actually it's going to be like this. So basically it's going to be soldered here. So basically this is going to be the printed circuit board, and it's going to be soldered like this. This is this kind of package. It's called small outline package. And basically usually have a number here, small outline package 14, means that it has 14 leads. Here, for example, if you have DIP 18, it means that it has 18 leads here. Basically, this we have 9 here and 9 there. And how about this? 1, 2, 3, 4, 5, 6, 7, 8. How about this? What would we call this? DIP? DIP what?
16.
1, 2, 3, 4, 5, 6, 7. Only 7 here. 7 times 2. So it's DIP 14.
14.
14.
Doctor, what's the meaning of DIP?
D1 inline package. Basically, D1 meaning that 2. Inline meaning that the leads are basically all in line. Basically, you put them all in one line. As opposed to something like this. This is QFP. QFP, basically, you have the leads basically like the size of a rectangle or something like, or a square. Okay? And basically, you have other leads. Actually, I'm going to talk about later. And basically, this is part of your project. Basically, is to look for leads, different packages. You have packages that look like this. Basically, just points here, like a matrix, on the one side of your IC. So basically, they would look like basically what they call ball grid array or PGA. Sometimes they call it this or this. Basically, they have leads here, but they are not really leads. They all look like a circle, half a ball like this, and basically you solder it to the board through this part here. This is basically the kind of leads that you would use in very high density components like a processor or things like that. We're going to talk about this later. Don't worry about it. But for the resistances, you don't have many packages. You usually have such packages like 2 lead packages or something like that, like the surface mounted or the through hole. And basically you can have for the through hole, you have the usual resistors that look like this. This is called the axial leads, which meaning that basically the leads are basically going through the axis of the cylinder that makes up the resistance. So consider this as a cylinder. This is a cylinder, okay? The axis of the cylinder going this way, right? The leads here are going exactly in the axis direction. In this one here, you have a cylinder also, but actually the lead is going in the radial direction, in the direction of the radius. This is a circle, and the basic is going in the direction of the radius, not in the direction of the axis of the cylinder. Okay, so basically this is through hole with axial lead, and this is through hole with radial lead. You have surface mounted, which is exactly the same as all of these components. You have the single inline package, which is this one here. Single inline meaning that you have leads on only one side, just one side, you don't have 2 sides. And usually this can be resistors that look like this. Basically, it can be either each 2 of these make up 1 resistor, or sometimes each one of them makes 1 resistor, and one of the leads actually is a common, like this. Okay, sometimes you need things that are integrated like this for some applications. Okay, you can have also D1 inline package resistances where you have, for example, each 2 opposing leads will have a resistance between them, or you might have all of them connected to resistances, and one of them is common, which actually is also used in some applications. Okay, so basically it depends on the application that you are using. Basically, you can choose any one of these. Sometimes it's a good idea if you're using a lot of resistances to choose one of these packages because they are much more integrated, and the matching between the resistance values will be much better than getting discrete components individually. Okay. There is also one different type of components which is called leadless components, which is exactly the same. It looks exactly like this, but actually it's leadless, doesn't have leads. And basically the parts here and there can be actually soldered directly to the surface of the printed circuit board. But actually they are not very common. These are not very common. They are basically surface mounted components are much more common in practice basically. So now do you understand what the meaning of component leads?
Doctor, I have a question about the
yes.
SOP14. Is it considered a surface mount?
Yes, definitely, because actually it's soldered in the same side. If it's like this and go through the printed circuit board, then this is a through hole. This is the only way it can be a through hole. Now, basically here, you're soldering everything here. So you can have on the other side of the printed circuit board, you can have another component here, for example. And they have no conflict with each other, okay? So the through hole is basically you have to have leads that go through a hole in your printed circuit board. So you basically put it from this direction and basically solder it so that you can actually use it in this particular printed circuit board.
So for example, if we want to classify SOP14, we would say it's dual line surface mounted.
Yes, but actually this is small outline because actually D1 inline is usually used for through hole. These are standard terminologies, by the way. Okay, so if you say that SOP, basically it means that it has to be like this, and basically it has certain dimensions. The dimensions of the SOP package is a little bit smaller than the D1 inline package dimensions. Okay, so basically if you talk about D1 inline package, people assume automatically that you're talking about a through hole component. And this is one of the important things that I want to bring to your attention if you are, for example, ordering a component from abroad. Okay, we're going to see that in a short while. Basically, you have to specify which package you want. Maybe in my first time, when I first started with my students in my project like 20 years ago, something like that, we usually order the components that we find online, and basically we didn't care much about which package we order. And this was a problem because if you get a component that looks like this, it's going to be really difficult to use it on a breadboard. It's impossible, almost impossible. You have to basically solder wires to each one of these leads in order for you to be able to use it. And we ended up basically creating a printed circuit board that we solder this on, and then the printed circuit board actually is connected to wires or something like that, so that we can actually use these wires on a breadboard. So if you order a component that is not dip, or if it's not through hole, you're gonna be you're gonna have a lot of problems when you try to use it for prototyping on a breadboard. Okay. So it's very important to identify these kinds of packages. This is one of the first things that you're going to do in your project, which is basically identify these packages, so that when you order a component, you order it specifically for the particular purpose you're planning to use it for. Okay? If you order it in a different way, you're going to have a lot of problems using that component. Is that clear?
Yes, it's clear.
Okay. Okay. When you try to order a resistance online, you have to have certain specifications for you to specify exactly the type of resistors that you need for your application. Of course, you need to have, the first thing, of course, is the value of the resistance itself. Okay, you need to know exactly how much, if you have 4.7K or 4.7 mega or whatever, you need to specify the value of the resistance, of course. You have to specify the package and the mounting, basically the type of package that you have or you want. If you, for example, need something to use on a breadboard, then you have to have it as an axial component, for example, and the through-hole component. If you need it for a particular printed circuit board that you designed, you have to specify it for exactly the size that you design your printed circuit board for. Or if you want to replace a component from a printed circuit board of a device or something like that, you have to exactly match the one that you have. So basically, you have to specify exactly the mechanical package or the shape of the component that you're going to order. Of course, you have to specify the tolerance. The tolerance is like the 1% or the 5% and so on and so forth. You have to specify the power rating. The power rating meaning that if it's for a quarter of a watt or a half watt or 1 watt or whatever, because actually if you bought a resistance for a lower power rating than the one you have or one you need in your application, you might end up burning, or you might end up with your resistance being broken or basically being damaged after a while, after using it for a while. Okay, the power rating is very important. You have to actually know how much current is going to flow in your resistance, particularly if you're working on a power electronic application. If you're working on a signal application, like if you're doing an amplifier or anything like that, this is not a problem. You usually have a very small rating for such resistors. But if you're talking about a resistance that is used to control, for example, if you have a triac or you have a power control device or something like that, and you're going to have to have a current of like tens of amperes or something like that, then it's a big problem, and you have to exactly specify what power you have to have in your resistors. Sometimes you worry about the temperature coefficient. If you're going to have a device that works in a condition, for example, if you're going to have a device that works outside in Saudi Arabia in the summer, okay? Then if it's exposed to the sun, then you would expect the component to have a much higher temperature than the one you have in your lab, which means that if the temperature coefficient is large, the value of the resistance might deviate a lot from what you would expect it to have in your lab. So basically, you have to worry about that if you're going to design a device that will be installed outside or in extreme temperatures, like for North Pole or something like that. You have to worry about the temperature coefficient. Sometimes you have to worry about something called stability or drift. Let's leave this until we talk about it in the sensors part, because this is very important. It's a nice concept that we need to talk about it in much more detail. The noise value is also important, and basically it depends on the technology of the resistance. But usually, as a rule of thumb, if you have a larger resistance, it will have a larger noise. Okay. Basically, it's usually recommended if you're trying to design a circuit, it's better to keep your resistors in the range below 10K. If you go above 10K, then you're risking to have more noise in your circuit. Okay, so So if I'm designing an amplifier, for example, if I consider like an inverting amplifier, very simple inverting amplifier. Okay, you have here RF and you have here Rin. Okay, the gain here V out over V in will be equal to minus RF over Ri. Okay, I can, for example, if I need this to be like minus 100, I can design it to be minus 100K over 1K, or I can design it to be what? 10K over 100 ohm. This is okay. This has a much better noise figure. This has a much higher noise figure because you're using larger resistance like 10K here, 100K here. Okay. So basically, it's better to keep your resistors below 10K as a rule of thumb for the noise. The last thing we need to talk about, but this is actually not going to talk about it in much detail, but you need to know about is the parasitic effects of your resistance. Basically, what we assume is that when we buy resistance, we buy something that looks like this. What we actually buy is something that actually looks like this. It has a capacitance, which is basically a stray capacitance between its terminals. Basically, as we're going to talk about it in the capacitance part, basically the resistance practically looks like this, right? If you have two conductors facing each other with a dielectric in the middle, with an insulator in the middle, then this is a capacitor. It might have a very small value, but actually this is a capacitor, okay? The problem with capacitors is that the impedance goes like 1 over j omega c. If you have very large frequency, then the overall impedance of the capacitance becomes very small, and basically is going to affect the value of the resistance. And this is actually something to worry about when you're trying to design a high frequency circuit. Okay, so this is very important to consider. So you have a stray capacitance between the components, between the terminals of the component, and basically this sometimes cannot be ignored. And you also have some kind of an inductance. Usually, if you have a wire wound resistance, sometimes, or some types of resistors are made of wire that is wound like this. Basically, it's just going to be exactly using the equation that we just talked about, rho L over A. And basically, we increase L by having more turns so that we have the particular resistance we want. Okay, so basically, if you have a resistance that looks like this, it's definitely going to have an inductance. And this inductance also can worry you in some cases. You have to consider its effect in some cases. But actually, this is very difficult to specify because actually you cannot specify the magnitude of the effect of parasitic capacitance or parasitic inductance unless you know exactly the kind of frequency and the kind of situation you have in your circuit. So basically, you're never going to find this when you try to order a component. But actually, this is one of the things that you have to consider always. So basically, let's now try to look at if we actually go and find a particular resistor. If we try to go and order resistance from DigiKey, for example, one of the largest distributors of electronic components in the world is DigiKey, www.digikey.com. I basically put the link in the last page of this presentation. So basically, if you basically select a resistor, just write here a resistor, and then select from under resistor through hole resistors. Here you find, as you see here, you have so many different parameters to choose from. Of course, the manufacturer, basically you have different manufacturer, you have a different package here where you can get your components, you have a different series, you have a different, basically the value of the resistance itself is right there in this part here. This is the value of the resistance. And you have the tolerance. You have, as you see here, it goes from 0.001% to all the way to basically, if you go down, you're going to find 10 and 20%. You have power rating here. You have a composition. You have a different composition. You have different materials where you actually, where the resistance is made up of this material. Sometimes, if you have a metal film, it's going to be different a little bit from a carbon film. Sometimes the stability and sometimes you need a particular type of resistance for a particular application, but actually for us, it's not going to be that big of a deal. You will have also here temperature coefficients. You're going to have here the operating temperature. This is the range where the temperature does not affect the construction of the resistance, which is basically usually a very wide range, like from -65 degrees centigrade to 250, which is really wide range. You have here the package that we talked about, axial, radial. You have all kinds of packages here. You have basically the size and dimension also are mentioned here so that you verify that you have exactly the size that you want. So basically, in order for you to order a resistance, you have to specify all of these actually, in order for you to completely specify your resistance, which is actually, you have to keep that in mind. If I talk about chip resistors is a surface mount types. Okay, so basically you're going to have here also basically the tolerance is exactly the same, the power is the same, the composition is also there. You have the package case, basically the thing that we talk about. Remember that the smallest one we saw was like 0204. There is actually a 0102 also. It's a smaller one than the one you saw actually. So basically this is very small components, and basically you have all kinds of different packages to choose from. And so basically you can also choose the temperature coefficient, you choose the operating temperature range, you have the packaging, where basically the packaging here meaning that basically how are you going to get your components. Bulk meaning that you're going to get your components like discrete components, like for example each one separate from the other. If you have a tape meaning that the components are actually adhesive, basically connected with an adhesive to a tape. This is usually what a machine, an assembly machine uses, okay? Tape and reel is exactly the kind of components where the automated assembly lines actually use. So basically you put the tape in its place basically, and the machine would actually take the resistances one by one and basically attach it to the place and the printed circuit board that you want. Basically for components that we use on breadboards, for example, you're going to find it in a tube. Sometimes if you have a DIP package, you find it in a tube. Tube meaning that it basically the components are placed in a plastic tube and you can take it one by one. Sometimes you can use tubes also on assembly lines. So basically you have many parameters to choose from if you want to choose a surface mounted component. If you're talking about a variable resistance, if you move to a variable resistance, or a potentiometer, sometimes people abbreviate it as POT. POT meaning basically it's a potentiometer, but it's just an abbreviation. You might have things that look like this, which is called trimmer. The trimmer is different from a regular potentiometer, is that the trimmer needs a screwdriver in order for you to change its value, like this one here, like this one here, like this one here. You have to use a screwdriver to change the value of the resistance, okay? Here, you can put a knob here and basically move it. And basically, it's exactly like the potentiometer you use in the lab. If you ever use a potentiometer in the lab, this is basically the same type. So basically, these are usually made from either carbon or wire wound. Basically, it's made of metallic wire. And basically, it can be used as a rheostat or a potentiometer. And basically, the difference we talked about, the rheostat has two terminals. You don't see exactly what happens in the middle. So basically, if this is a rheostat, then it would have only two terminals. And basically, the value of the terminal in the middle, or the resistance between this terminal and that terminal, you'll never know. Okay, you know only the resistance between here and there. And basically, because it's connected to one side, so basically this is short-circuiting this part of the resistance. So from this side here, the resistance is 0. All the way to here is exactly the full value of the resistance. This is basically the range of the rheostat. For the potentiometer, you have three values. You have three leads like this or like this. Most of the potentiometers actually have three leads like this. So basically, you have the two leads, the two main leads, and the resistance between these two main leads is exactly the same because it's a full resistance. And depending on the position of the slider here, you will have different values of your resistance between this and this, or this and that. One very important thing is that you might find the resistance of the potentiometer to be either linear or logarithmic. meaning that instead of increasing the resistance in a linear fashion like this, it might increase in a logarithmic fashion like this. Logarithmic potentiometers are very useful in such things as, the volume. If you have a volume knob in your MP3 player or whatever, or any device like, if you talk about anything that has audio, for example, the perception of humans is logarithmic, is basically proportional to logarithm of the intensity of the sound, okay? So basically, when you increase it linearly, you're not gonna find it to be basically increasing the way that you are used to. Usually use a logarithmic potentiometer in order for you to be able to basically increase in a manner that would be felt like if you increase it by double, for example, you feel that like it's double the intensity of the sound. So basically, be careful when you're ordering a potentiometer to make sure if you wanted a linear potentiometer, to get it a linear potentiometer or a logarithmic potentiometer, you can also make sure that it's like that. If you also go to DigiKey, and this is actually I want you to do yourself, just go and find that. Basically, also made a search by variable resistors, and basically it shows rotary potentiometer rheostats. Here, for example, let's see the function here. You might find it as a linear, logarithmic, or reverse logarithmic. Reverse logarithmic, like it's the inverse of logarithmic. So instead of having a curve that goes like this, it's going to go the other way like this. Sometimes you have, if you want to compensate for the sound coming from a mic or something like that, in order for you to save it in a linear fashion or something like that, you might need to have a potentiometer or put a potentiometer like this in an amplifier so that you can actually convert the logarithmic into a linear curve. And you have also the number of, you have also the power, you have the tolerance, you have the value of the resistance itself. Of course, you have different, now the rotations actually, you might have continuous rotation. Continuous rotation meaning that it's basically the knob keeps going clockwise all the way, without even have an end, basically. You might have a range, for example, like 120, meaning that basically you have the distance between the start and the end of the scale is like 120 degrees. Sometimes you have it like 260. So basically, it depends on the kind of application that you need. Okay, so basically, it's very useful to go to DigiKey and look at the actual components and basically learn how to choose these components, because you might one day need to do that for your project, for your work after you graduate, and things of that sort. Is that clear?
Yes.
Yes.
How much time do you have?
It's 2:13.
It's 2:13, yes. But I mean, how much time do you have? How much do you have another class after this one?
I have another class.
At what time?
2:30.
2:30. Okay. So let me talk about 2 slides, and basically we stop after these 2 slides. Okay. So it's gonna stop at 2:20. Okay.
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 Okay, no problem.
Okay. So basically, I'm gonna talk to you about 2 types of nonlinear resistors that are very common. One of them is a light-dependent resistance, which is sometimes called LDRs. LDRs look like this. Basically, they are made of a particular material that contains very few electrons. When you keep it in complete darkness, its resistance will be really high. When you expose it to light, the light will give the electrons energy and basically make them liberated. And basically, whenever you have free electrons liberated by this process, then it will become more conducting, and basically the resistance will be a little bit small. So basically, the typical dark resistance of an LDR is between 1 and 10 mega ohms. A typical light resistance is between 75 and 300 ohms. So this can be a really nice sensor for light. So this can be used, for example, if you want to, for example, open the door of a mall or something like that, when people come or something like that. Basically, you have a light and you have one of these sensors, and whenever somebody crosses the line between the light and the sensor, basically it generates a change in the resistance, and you can detect that change and make the door open, for example. Okay, so this is a really nice optical sensor, basically, or light sensor. Okay, One thing to keep in mind for this resistance or this LDR is that it takes some finite time to change its state, and this time is called the recovery time. Meaning that basically this will be exactly the same resistance. Its resistance is going to be like one ohm or 1 mega ohm. And for example, assume that it's 1 ohm, and it's going to be like 300 ohms. It's not going to change from 1 mega ohm to 300 ohms instantaneously. It's going to take time. And this time it's called the recovery time. And the typical recovery time is about 200 kilo ohms per second. For example, if I'm talking about going from 1 mega to 1K, okay, then basically you're going to go down from this to this at a rate of 200 kilo ohm per second, meaning that after 1 second, this will be 800. After another second, it's going to be 600, then 400, then 200, then 100, and so on, basically. And then after that, you basically, after 5 seconds, you're going to be close to the 1000 ohm value that you have. And also, if you move the other way, it's going to be exactly the same. The recovery time is basically for moving this way and that way. So basically, that change here is not instantaneous, basically. So you need time in order for the resistance to change. Okay, from dark to light or dark to light, from dark to light or light to dark. Okay, so this has to be kept in mind because some applications need a little bit faster response time. So this is a type of a non-linear resistor because basically it depends on something that you have no control over. So basically it's exactly the same resistance. If you're flowing a certain current, the voltage will change depending on the light, which is a very different thing. It's basically, it has nothing to do with your current, and basically that's why we call it a nonlinear resistance. The other type, which is going to be one of the things that we talk about in detail, is temperature-dependent resistors or thermistors. Thermistors are basically made of semiconductors. They have really, as you see, very nonlinear characteristics like this. So basically, this is the temperature and this is the resistance. The resistance changes with temperature in a very nonlinear manner. But the point is, basically, you can actually put the equation like this. This is the resistivity of the thermistor for the NTC type, the negative temperature coefficient. Here, actually, the resistance decreases with temperature. Here, the resistance increases with temperature. So you have negative temperature coefficient thermistor and positive temperature coefficient thermistor. Basically, you can have this equation here for the negative temperature coefficient thermistor. Basically, they are inherently nonlinear. And basically, you can linearize it somewhere. If you look at a particular range, for example, if you talk about for the range from 0 to, for example, 50 degrees or something like that, it's really very close to being linear. So basically, you can use it in different applications, like in medical devices, like in things of that sort. They are really very useful. They are not very expensive. They are really very low cost, and they are really very useful. We're going to talk about them in much detail in the sensors part. But I just wanted to talk about them very quickly now, just to give you an idea about a nonlinear resistance. It's nonlinear, again, because basically it's exactly the same resistance. If you consider this as your resistance, if you flow a particular current here, the voltage will change depending on the temperature, which has nothing to do with electricity, basically. So the resistance itself has basically can change with other things that are unrelated to the electric current flowing in the circuit. So basically, it's a nonlinear resistance. Any questions?
Doctor, you mean the thermistor is only change the voltage change in the terms of temperature or what?
It's the resistance changes as a function of temperature. Basically, the curve is like this. Basic for NTC, it goes down like this. For the PTC, goes down like this. Their usual resistance, basically, if you have a resistance, basically the usual resistance is actually going to be like this. The curve is going to be linear like this. Okay, so basically it changes the value depending on the temperature in a nonlinear manner. Okay, we're going to stop at this point right now. I'm going to stay. If you have any questions, I'm not going to explain anything more. If you have any question, please stay and ask me the question that you have. We're going to have another lecture. We're going to have lectures every Sunday, Tuesday, and Thursday, every week, because we don't have labs now. And hopefully we can, probably by the end of maybe next week, not next week, the week after, hopefully we're going to be close to finishing the material, and basically we're going to start reviewing for the final exam. Regarding the mock exam or the test exam that you're going to have before the midterm exam, basically I'm going to have it on Wednesday at 9 p.m. Would that be okay?
Next Wednesday?
Next Wednesday.
Okay.
On the blackboard.
And the actual exam will be on Saturday, anytime you want. What time would be suitable for you on Saturday?
Saturday at 9.
The what?
8 p.m.
8 would be a little bit early for some people. Would it be
Okay.
possible to have it from 10 to 12?
No,
No,
I mean
it's good.
No, from 9.
9? Okay, 9 is fine. Okay. So we're going to have a mock exam or a test exam or practice exam on Wednesday. Just for you to test, how the setting will be like, how are you going to solve the problems and submit them in time and things of that sort. And then we're going to have the actual midterm on Saturday, inshallah. Okay?
Doctor, will it be on Blackboard?
Yes, it will be on Blackboard. That's why we need to have it at night and on Saturday, because otherwise we have no guarantee that the system will be reliable enough to allow everybody to submit their exams. If the system closes and the student cannot, finish solving the problems, basically it's going to have a timed exam, meaning that if the time passes, the student will not be able to submit the exam at all. So basically, we have to choose times where the system servers are not loaded.
Okay.
Doctor?
Yes.
Can you please upload all the information on the Blackboard?
Yeah, sure, definitely. I'm going to do that. I wanted to agree with you on that before I do that. And the lecture of next Thursday, the lecture right before the exam, will be for a review lecture, basically. So next Thursday, all I'm going to do is basically solve practice problems or basically answer your questions about the material that is included in the exam. Okay? Again, the exam will be all the way up to the oscilloscope, as I said before. Okay?
Okay.
Including the
Doctor?
Yes.
Yes, how about on Thursday we solve the mock exam?
Thursday, it's up to you, whatever you want. Actually, the mock exam is going to be basically just, I'm going to pick some examples from the practice problems and that's it. But actually, if you want me to solve them, it's fine. That's fine. No problem.
Okay.
Okay. I'm going to post the recorded lecture from now on Blackboard so that you have a copy of it if you want to, review it for any reason. The current lecture, which is an updated version of the previous one, is already there. And I'm going to post the homework so that we go over next time, inshallah, after we finish this chapter. Okay? Okay?
Okay.
Okay.
Any questions?
Yes, doctor. Was there any attendance taken?
Actually, no, because actually, I know the difficulty that everybody has actually. So basically, I'm not gonna have any attendance for these lectures because already the lectures will be online and you can review them. But I would actually encourage everybody to be to join the session so that you can ask the questions instead of going over the recorded version and having questions and you have nobody to ask. So basically, attend so that you can ask your question during the session.
Okay, thank you.
Okay, shukran. Okay, see you inshallah on Sunday, inshallah.
Inshallah.
Salam alaikum.